Welcome to the Walton Pi. Today we are going to be talking about arithmetic modulo n. In a previous video we talked about the integers mod n, and this is going to be continuing that to figure out how we can be able to do different arithmetic operations in the integers modulo n. If you need a refresher, check out that video before you watch this one. So, to start off, we need to refresh our definition of what it means to add and multiply in the integers mod n. So, if x is the class of a and y is the class of b in the integers mod n, so reminder, that means that everything in the class of a is congruent to a modulo n, meaning that a divided by n has the same remainder as any other element in the class of a when you divide by n. We define addition and multiplication on the integers mod n by saying that if we have the class of a plus the class of b, that's going to be equal to the class of a plus b, and then multiplication is defined in a similar way, where if we have the class of a times the class of b, that's going to be equal to the class of a times b. So if we want to have subtraction, because we currently only have addition and multiplication, we define subtraction as adding the additive inverse. So the additive inverse is whatever element adds to x to give us the 0 class, or 0. So if x is the class of a, y equaling the class of negative a is going to be the additive inverse. So a minus b is equal to a plus negative b, which is the same thing as the class of a minus b. Now, if we want to divide, this is where we run into a lot of challenges. In the integers mod n, division is not allowed. We are allowed to add, we're allowed to multiply, and we're allowed to subtract, but there's no way to define division so that it will always work. However, sometimes there are multiplicative inverses, kind of like the additive inverses that we had to define subtraction. And so if we can have a multiplicative inverse, then that means that we can multiply by the multiplicative inverse, kind of like how in subtraction we added the additive inverse. If we have multiplicative inverses, then we can multiply by those inverses in place of division. However, multiplicative inverses are not always guaranteed. So, a multiplicative inverse exists for a value a in the integers modulo n if the GCD of a and n is 1, meaning that a and n are relatively prime. So to find the multiplicative inverse of a, we have to run the extended Euclidean algorithm to be able to write 1 equals ax plus ny for some integers x and y. If you need a refresher on how to do that, check out the video in the card. So here, if we can write 1 equals ax plus ny in z mod n, x is going to be the multiplicative inverse of a. So anytime we would need to divide by x, or we would be wanting to divide by x, we are going to, anytime we would want to be dividing by a, we are going to multiply by x. Because we're not allowed to divide by a, but we are allowed to multiply by x, and it turns out that multiplying by x behaves as if we were able to divide by a, except it is a valid operation in the integers modulo n. So let's say that we are in z mod 12, and we would need to solve the linear expression 5x plus 3y 5x plus 3 equals 11 modulo 12. So to start off, we would subtract 3 from both sides, because subtraction is a valid operation, and we get 5x is congruent to 8 modulo 12. We're not able to divide by 5, but we could multiply by the multiplicative inverse of 5, which in this case turns out to be 5. It's not always itself, it's just itself in this case, because 5 times 5 is 25, which is 1 modulo 12. So we can write x is congruent to 25x, which is 5 times 5x, and since we know that 5x is 8, we can replace that with 5 times 8, which is 40, which is congruent to 4 modulo 12, which tells us that x is going to be 4. We can then test that where we can plug in 4, so we get 5 times 4 plus 3. That gives us 23, which is congruent to 11 modulo 12. Now here's an example which shows why we need to have multiplicative inverses to guarantee a solution. Let's say that we were solving pretty much the exact same thing, except instead of a 5x plus 3, it is now 6x plus 3 is congruent to 11. So, again, we would subtract 3 from both sides, and we'd get 6x is congruent to 8 modulo 12. But when we try and find the multiplicative inverse of 6, there isn't one. We can't find any valid multiplicative inverse. And when we go and try and just plug and chug to find if there are any values of x that work, we find that no value of x is going to work for this, which tells us that if we don't have a multiplicative inverse, we might not actually have a solution. Now, that doesn't say that every time that there is no multiplicative inverse that there are no solutions, because we can also have more than one solution. So, if we were trying to solve 4x plus 3 is 11 mod 12, we'd subtract 3 and we'd get 4x is congruent to 8 modulo 12. And when we try and find the multiplicative inverse of 4, we again find that there isn't going to be one. But in this case, there's more than one solution. X equals 2, x equals 5, x equals 8, or x equals 11, all of those would work. So just because there isn't a multiplicative inverse doesn't tell us that there's no solution. It also doesn't tell us that there's going to be more than one solution. All it tells us is that we can't divide. We have to find a different way to be able to go about and solve the problem. So every time that you come across these, hope that you have the situation where you are able to have a division of sorts, where you can be able to multiply by the multiplicative inverse. But recognize that if a multiplicative inverse doesn't exist, then you might have no solutions, or you might have more than one solution. I will talk about this in a future video, just not in this one, so keep your eyes out to be able to see that when it comes. I hope this video is helpful for you, and that this was able to help you understand how you're able to add and multiply in the integers mod n. Please check out some of my other videos, and please like and subscribe if you haven't already. It helps me out quite a bit. Have a great day, and good luck with the rest of your math.